Hi, in this video, we will do conformation analysis of substituted cyclohexanes. So as of this point, we should know that every cyclohexane would have different conformation to them, and the most stable one are the chair conformation. And within the chair conformation, there are two chair conformations that are flipped of each other. And so basically, a substituted cyclohexane would exist primarily between these two chair conformations right here. And the two chair conformations are not equal in energy because in the two chair, it's possible that this group will be facing axial or equatorial. And whether the substituent group are axial or equatorial, they would have different steric energy to them and therefore are not equal in energy. And the steric energy that destabilize the molecule are then referred to as the destabilizing energy or ED. And the higher the destabilizing energy, then the less stable that conformation would be. And now, let's look at an example of what happened in the monosubstituted cyclohexane. So in monosubstituted cyclohexane, the ring will flip with equilibrium favoring the conformation where the substituent group is positioned at the equatorial position, not the axial. And the reason why is because when the groups is at the axial position rather than equatorial, it will possess a type of interaction that is known as the 1,3 A1,3 diaxial interaction. And here's what it is. So here is a monosubstituted cyclohexane. So when it exists in the chair conformation, it can go back and forth between the two flipped chair. But in one of the flipped chair, this substituent group right here, when it facing at the axial location, it will be come in and interact with the two other axial hydrogen in this other carbon right here. And this interaction right here is then termed the A1,3 diaxial interaction. And the reason why that we call this A is because first A here refers to the axial location. And the 1,3 here is because this R group right here and the hydrogens are basically 3 carbon away from each other. So let's say here carbon 1, carbon 2, carbon 3. So this will be interacting with the hydrogen at the carbon 3. And same thing over here as well. This R group would also be interacting with this hydrogen, since there are 1, 2, and 3 atoms from each other. And therefore this is called A1,3. And now RH here is to show that it is interaction between the hydrogen and the alkyl group. So when the substituent group locate on the axial location, it has this interaction right here that destabilize the molecule, and therefore this is not stable. And therefore the molecule will flip to produce the other conformation that would make it more stable. And so the equation to calculate this energy right here and will be as follows: ED equal to A, in this case 1,3 R and H. So that's how we can label it. Now let's look at an example right here. So let's say the R group equal to methane, to a methyl group. So now let's calculate how much energy involved between the two chair conformation of this. And again, we're only interested in the chair conformation, since the chair conformation would then be the most stable conformation for any cyclohexane. But again, there are two chair conformation and they flip of each other. So let's see which chair conformation will then be more stable. And now we can get started by drawing the first chair conformation. So in this case, let's do it. So let's draw the first chair conformation. And again, make sure you follow the instruction and draw this chair conformation very well, because when we analyze the structure of the chair conformation, getting the group at the right position is really important. Okay, so now we first started by having drawn two slanted lines. And now we would again imagine the horizontal line touching the top line, and this is where we're going to put the dot. And same thing down here. That to be the horizontal line, and now this is where we're going to put the dots. Ready? And now we're going to connect the dots. So these two dots connect, and same thing here. So there you go. And now let's label the carbon so we can follow this. So here in this case, let's call this carbon 1, carbon 2, 3, 4, 5, and 6. And now this is where we're going to put carbon 1. So again, it does not matter where we start numbering, because what we're looking at depend on a numbering with basically different view or different rotations of the same molecule. And now let's put this carbon 2, 3, 4, 5, and 6. So in this case right here, when we have this methyl group right here, this methyl group right here can either face up or face down, right? So in this case right here, let's do that. So let's put this one right here, pointing up. And now let's put in the rest of the other hydrogen. So here in this case right here, we can have hydrogen right here, one hydrogen right here, and for this carbon, one hydrogen right here. The other hydrogen will be pointing up. And for this one, this will be its axial hydrogen, and this one right here will then be its equatorial. So that will be all of the hydrogen on the left side. And now for the one on the right, for the other half of the carbon on the right, this will then be its equatorial location, and after the hydrogen, it will now be pointing down. And for carbon 3, this will then be its axial, and equatorial will then be right here. And for the carbon 2, this will be its equatorial, and this will then be its axial. So this will then be the structure of one of the flip chair. And now here in this case right here, we will then see that the CH3 group right here, it is at the equatorial location. And now let's flip this and see what happened. When we flip this, so again, to draw the flip chair, because right now we are slanting this to the left initially. So when the flip chair will be slanted to the right. And again, imagine the horizontal line and make a dot. So that will be right here. And then the other horizontal line, that will be right here. And now we're connecting the dots. And there you go. That will be the other chair conformation. And again, number this 1, 2, 3, 4, 5, and 6. And now let's see what happened to the methyl group, to the CH3 group. So here in this case right here, right now this group right here is equatorial and point up. So when this flip, this will remain up and will be on the axial location. So that's where this methyl group will be. And the hydrogen will be right here. And now let's put in the rest of the other group. So for the carbon 2, the hydrogen at the equator will be there, and the axial will be here. And for the hydrogen 6, this would then be its equatorial, and this would then be its axial. And for carbon 3, this would then be its equatorial, and this would be its axial. Carbon 4, hydrogen 4, 30, and for carbon 5, again, make sure it's equator to the right, and this would then be its axial location. So this would be the two different conformations of a monosubstituted cyclohexane. Okay, and now let's figure out which between these two conformations right here, which one will be more stable. So when we compare, when we look at the right one, now we have this methyl group right here. This now come in and interact with this hydrogen right here, right? Because this is in the axial location, and this basically exhibit this interaction that we discussed up here earlier. When we have a group at the axial location, it have this A13 diaxial interaction right here that we mentioned between a CH3 group and the hydrogen. So because this CH3 group right here is now interacting sterically with this hydrogen, and also interact with this hydrogen as well. Now, we do not consider the interaction between the hydrogen to be significant because first of all, they're too far away from each other. And also they exist in every type of conformation that does not matter which one that we draw. So therefore, by default, we will eliminate that and set that equal to 0. But we only consider the other one involved in the group, because that is uniquely different in the different conformation. So in this case, this is what it will have. So there versus over here, this do not have that. This conformation do not have the A13 diaxial interaction. So therefore, we would expect this to be more stable. And in comparison, this it will then equal to 0 kcal per mole. Versus for this one, it have this A13 diaxial interaction between the CH3 group and the hydrogen. And this value right here turned out to be, so each of this interaction right here is 0.8 kilocal per mole. 0.9 kilocal per mole between the methyl group and each hydrogen. And in this case, this has 2 of it. So therefore, this value then equal to 1.8 kilocal per mole. So in comparisons between the destabilizing energy between these two conformations, one is 0 and the other one is 1.8 kilocal per mole. So this one right here will then be more stable. And going back to this statement of what we have seen earlier, whenever the cyclohexane is monosubstituted, the ring will flip with equilibrium favoring the position where the substituent is facing in the equatorial location. And this is what this is referring to, because that is when we have no steric energy or destabilizing energy to it. And in fact, if we were to look up data, then this molecule would exist in this conformation 95% of the time, versus this one right here, only about 5%. Make it this one more stable.